No, this is the university. Please make a tour to all the way to the eye. You will find this gate. It's really beautiful. Yeah.
I saw just back here.
Excuse me, Bruce. Okay. Hello. Hello, dear conference participant. It's my pleasure. So today, today afternoon session, I will be chair of this session. So, and the first talk of afternoon session is of Professor Song. His talk will be about the search for the dark energy in the universe. Professor Song, you have 40 minutes to talk and 10 minutes for questions and comments.
Yeah, so I'll be in time. I'm going to talk about all the effort to search for the dark energy, using LSS representing for the large scale structure of the universe. Then I define what is this in the how we can observe in the talk in very detail. To begin with, people actually just say thank you for organization, but really truly thank you for the organization. It's a really nice arrangement. I can see all your effort in the behind this conference. I actually take the picture when the Eric guided us, but unfortunately the sun was located here. My picture was ruined, so I just stole the one picture from the Google image. I'm from the Kaji and representing the Korea Astronomy and Space Science Institute. So as the name says, we are non-university and we are institute, like 150 staff, major in astronomy and space science. And then in the institute, and we define our group as a course Kaji, and then course represent cosmology. So means the cosmology group inside and the Kaji. So I think that it would be the good. I little bit change my plan since I visit and talk with you the last Monday, because I found some similarity with our effort and your effort and through Eric. So let me briefly introduce the cosmology group when we started and then how we are going. So this is I said the pre-Koskaji, and the Koskaji was cosmology group started from the 2014, but in the 2013, I don't know what to do, but surely Eric know what I need to do, so we invite Eric as the faculty, as you do here. So actually we sit together and two-man's group, and what is our future. So, and one of his suggestion is that, okay, next year in the 2014, let's organize one international conference. It's exactly the same here. And then among the invited speaker, and I find some George Smith there. Probably you remember you come 2014, and he also sit here now. We actually get the momentum, and I thought the biggest the lucky thing through our progress was we get the brilliant faculty member. Actually, the Alman will visit here in the end of the September, and I really want to. We actually establish our collaboration in the future. So the other major challenge is that we need involving the biggest, the future experiment, and that was Eric's suggestion. Probably the righteous direction is going to large scale structure experiment, which initiated in the 2014. So we joined the Egypt, And then some effort and lead us, and then the define as some the big issue group in 2016. That is some of the core for the proposal in 2015 in Korea. All the science area, biology and engineering, everything, they actually define some of the big issue group like around 10. And then again, with the huge effort with the edit, and we actually pass our proposal, and then now it's funded in the next 10 years. So with this momentum, now actually we hire the one more faculty, and we sit in the middle of the very pleasant the building. It's but you don't have to remember this map. When I invite you guys to our institute, I send you this map again to give the detailed direction. So now I'm going to talk about some of the not actually my group activity, and then just my research in what I'm doing, and what actually Arman or David do, and then they will come here, and I'm already some of the scheduled visit here, and they will actually explain and one by one and slowly. So I started from the cosmic acceleration, and you already know we are in living in the university, we are accelerating. We don't need any more theory. There are so many brilliant ideas come to the table, and they're waiting for test what is true. And I think that we can actually, instead of proposing the new theory, and then I can actually summarize and then make a classify, and then what is typical thing. So I can see some of the typical the common theme was the theoretical model and the other theoretical model, and the one theoretical model easy just to put the cosmological constant or some of the unknown particle. You can add up something unknown energy component to the right side of the Einstein equation, or we actually test the gravity above 2 millimeter all the way down to the solar test, but we never test any gravity and beyond the solar system, galaxy, cluster, even the horizon scale. Nobody knows whether the Einstein gravity is still valid in that scale. So those who do not want to put the unknown component to the universe, then you can actually imagine this way. So Einstein worked in our solar system, and they put the gravity, but you guys actually now has some more data, and then so cosmic acceleration, and some people probably think this is kind of the signature of the gravity should be modified. So I just summarize one equation. Everybody hates the Einstein equation, but for the student it's just simple. So you just say there is something, the put energy and the matter on the space, and the space-time is curved. So in the left side, or in the right side, whatever you want to put. So you can put the energy component you know, or you can add up something unknown component, and then the known gravity response. Second class, you don't actually modify any types, just put everything you know on the right side. And you cannot just modify how space-time responds to your known. So it's something like that. You actually modify gravity, which actually introduce and change the left side. So now it's again is that whatever it may be, we need the observation to test which one is right. So now this talk, I advocate and I support large scale structure formation experiment. It's ideal, the tool in the future. At least we can tell whether we need unknown component and whether we need the modified the gravity. So that is actually my key point. So then gravity is something in response to this. Then let me actually introduce the large scale structure from the simulation. It's not the real world, and there is some huge box size, nearly close to some horizon scale, and I just some make the cut very small box. Here, the black part is just the empty space in the simulation, and here is the particle, and I assume this is the dark matter particle, and then the sparkling with the yellow light. And we actually run with the same initial condition, with the same, everything same, but the one actually, the running without the dark energy, and the other actually with the dark energy. And we say dark energy accelerating the universe, so what is the meaning? We actually weaken the gravity, so technically means that actually some of the physical explanation will leave the signature on the large scale side, and as you see, it's exactly some of the meet our physical intuition here without the dark energy and then stronger gravity. And if you see some of the void with empty space and get darker, and then the brightest part, if you compare each other and get brighter, what is the meaning? And when there's clumping and the clumping more, and then we actually see some of the stronger the gravity, the signal here. Now, with the same the initial condition, we running it with dark energy, and gravity seen in the weakened. The same point, and you see whether you agree or not, is slightly less bright, and the void is not clear, less clear. So, before we actually introduce some of the statistics or mathematics, and even we eyeballing if we observe the large scale the structure, then we can tell the difference. Now, because we are doing science and analyze some of the data set, what you are doing is just a confirmation of what you're seeing. So, try to define some of the density field in the small space, and we actually make like you actually measure the average. What you do after you measure average, you actually measure the dispersion, right? So we actually analyze dispersion and then the correlation, and we just confirming in the mathematical way and what we are seeing. This is my whole point of this talk. Now, this is actually theoretical model. Now actually we move to the actual observation. When you go to the observation, and the first the problem is that, can you actually see the dark particle in our eye? No, right? So actually, if you observe exactly like this, then the game is over. We analyze data set, and then everything done. But in the real world, this is it. It's a turned off in the nothing to be visible to our eye. So something actually hidden in the universe, and what's actually fluctuating the large scale structure, which actually reveal the secret of the dark energy or dark gravity is completely hidden. So our job, do you actually hear the echo? So our job is that how to reveal this when I actually make the introductory some of the talk about the large scale structure, and then I like this a lot. So let's actually compare with some of the waveform on the surface of the very clear. So as we are, as some of the large scale structure is invisible in the out there, and also as you see, it's so clean water, and then actually the wave fluctuation form on the water, we can't see it. And if you want to reconstruct the waveform, probably there is some two different ways. And the first one, you actually shed the light on the top of the water, and then you see on the actually wave is going up, then the light actually is going, and then the focus on the bottom. So there is some the light form was actually formed here. So if you do some the mathematics, and when you actually analyze the light pattern on the bottom, then you can actually reconstruct the waveform. That is called as a weak ranging experiment in the cosmology. And second part is that here is you see some the leap here. So this is more direct. If you actually some the spread the leap on the surface of water, then it's actually floating around, right? So leap is going up in the wave is up, and also the leap is going down in the belly of the water. So instead of you tracing the invisible the wave, you can tracing leaves on the water. Then actually you can see some of the invisible some of the waveform through the pattern of the leaf. So actually this talk I support second idea. So in the cosmology, this leaves is the galaxy. So we actually some observe the galaxy of the sky. We don't know, and then there's some invisible large scale structure, but where actually higher density and you expect more galaxy, and then there's an empty space in the hidden invisible some the large scale structure, then you don't quite expect any galaxies formed there. So it's not actually the true large scale structure, but it's a galaxy distribution. But actually you see some of the pattern. Probably this is matching to the large scale structure behind of the universe, which is invisible. So we use this and then we start to analyze the data. So and then before I go to the detailed the science, let me actually some of the review some history when it started, and then how is the developed. So I don't know exactly. This is the history of the galaxy survey, the origin, but I do believe, and the first galaxy survey has been done in the early 1980 by the CFA. They observed the 1,000 galaxy of the sky, but you are very familiar with any statistics. If you want to provide any trustable the result, we need a lot of sample. 1,000 is not quite enough, but still, when the data is released, was sufficient to get the attention from the people. Why? Because if you see this, and then people are just some of the interesting. This is a bubble picture. So the universe actually we observed from the sky seems like there's some of there's an empty bubble was surrounded by the filament. That was 1983, and after 10 years, and then the many efforts has been made, and then the number is get the 10 times. So it's by the end of the 1988, and we actually get the number of galaxy is 18,000. So here we see some of the clear filament structure and then the more clear void. So probably the universe is formed really from the filament structure. And one of the interesting thing from this data, and they also discover not only some of the filament structure, and they find some of the great wall of the galaxy. So, but still, number of 10,000 is not quite enough, which provide any some of the trustable the data set. Now, in the back by the 15 years ago, finally we reach the number of galaxy observed 200,000 with this radical the new technology of the spectroscopy effect. From this point, we finally apply our statistical the analysis and then provide something, although its error bar is really huge, what is actually statistical amount of the observation. So now actually we are in the 3 million the time by the 2015. Now we are in the doorstep to the precision cosmology. And everything was discovered, less than 10% of the error, the estimation. So we are here. So here I show you some of the footprint of the recent galaxy survey in the North Hemisphere. And then the little bit, the south patch of the here. Because the telescope was the seat on the North Hemisphere, we don't quite cover the South Hemisphere. Most the observation has been done here. Now, before going into some of the detailed discussion, I actually mention again about the Einstein gravity. So, here is some of the, so what is exactly meaning of the 30 million in the statistic? So here is the I compare with what we have done with 3 million the galaxy and with all the way down to the higher redshift and then each being in the future generation of the daisy, and we are end with 1 or 2% of the precision observation. What is exactly meaning of this? And then once we actually make the measurement throughout the higher redshift, and the two beginning, and I introduced cosmic acceleration can be accelerated by some of the unknown dark energy model and or unknown gravity. At least we can tell those differences. So in the end of the 5 years, probably we can say whether gravity is modified or whether we have to improve some of the new dark energy component. Now, precision is guaranteed, it's promised, but what we have to, what we need to do in the 5 years time is that we have to develop our theoretical model to meet this data set. Key point of our theoretical effort here is very simple. I show you some of the map in the real space, and I show you the map in the redshift space. So we have to make the predict, the accurate some of the prediction, accurate some theoretical model, how those are mapping to the other side. So here is the first generation in the 1987 by the Kaiser. He actually make a formulator with very simple design model. So delta represent density field and with the velocity of the theta, and the map should be modified in this way. So if we apply some dose prediction, this is a blue contour was actually measurement in the simulation, and then this actually the dot contour is actually theoretical model without any correction. As you see, probably is a good behavior in some region, but all the way down there, our theoretical model is completely mismatching. So if we don't improve this theoretical model, and technically we are not able to do any some of the extraction of the peculiar velocity. So from our understanding, then how we can understand this theoretical model is not quite complicated. So I actually start from the very simple, the Fourier space transformation. It's very simple. Probably in the college some of the mathematics, and we do know how this the real space, some of the field quantity and the Fourier transform and into some of the K space, the transformed some of the quantity here. So all the trouble is that x, the coordinate actually transform into redshift space. And what is the issue is that x plus, and we have some of the peculiar velocity, and this peculiar velocity, what is actually difference between the x coordinate and the peculiar velocity? X is a coordinate, but peculiar velocity was a stochastic quantity, right? So when the x is transformed into x plus peculiar velocity, but the peculiar velocity cannot get outside the ensemble average because this is a stochastic, it's not a coordinator. It cannot be going outside the ensemble average. We have to make appropriate the projection of this stochastic with observed quantity. That is only one thing we have to understand in this mapping formulation. Once we actually make it inside, and then we just discover that was originally 2-point correlation function, but as you know, when you actually expand the exponential term, which create many higher order, this higher order correlation create two troubles, and the first one, higher order the polynomial, which actually depend on axis separation parameter and between the two components, which should be inside the integration. Second contribution is that which is not the separation correlated part, which is 1 point the higher tower, which is not depend on the separation parameter, and it can be going outside the integration, which is understood as a finger of God effect. I told you what's the meaning. So now actually unfortunately, as you see, when you actually expand the exponential function and we end up with the infinity the expansion, so basically the mapping we want to understand is not given as a closed form, but actually is given in the series form. So we have to understand the truncation, whether we actually cut first or second order, or we need a third order. So this is our game. So actually we actually the start our test from the nonlinear correction. From this point it's a little bit some technical. So here black dot is a simulation, and the red dot is actually our understanding of the theoretical model of the nonlinear correction. It's not the mapping. Before we mapping, we have to understand some of the nonlinear correction term. We actually include the one loop correction term and the second order the correction term. And our theoretical knowledge of the nonlinear correction term is breaking here. But actually, we find some of the idea. So second part is that the contribution from the 2-point correlation. So set aside the nonlinear correction part, and we actually we actually derive all the higher order polynomial due to some of the depend on the correlation the part. So here actually some of the zeroth order when there is no impact from the velocity field, and we actually collect the second order, and here we actually also collect the second order. So including this all the expansion, and this is known and some part is known, and couple of part, and we actually discover in the newly, and we actually include. So actually we decide we truncate up to the second order. And second one is we actually name this ABT part, and then we have to the test. So if those the separate part, we actually the measure AB term, and also we actually the measure tri-spectral part. So I don't go any detail. So then how we can understand before we go into some of the not correlated part, and we actually have to test whether those components is safely some of the cleaned. So we actually make a subtraction of our older correlated part, and then which actually give some nice k-mu dependence. So technically means that independent of the scale, everything was aligned in the k-mu the space. So technically means that all the separate the distance part was completely cleaned. So second, the last part, after we actually clean up some of all the inside integration, and we also take outside the finger of God effect, and then As you see, the finger of God effect itself has some dependence on lowest order and the highest order, and then we actually formulate some the Gaussian formulation, and we derive the finger of God effect form is a perfect Gaussian. So as a timer, and I actually jump to the final test. So here, we actually test whether our theoretical the modeling is working or not with many different the simulation. We actually make a simulation with the omega lambda is this value or all the way to the different value. And the first one, I actually skip this part. So this is actually the indication of the peculiar velocity growth function. When we actually measure, the template is the calculator using some fiduciary model. When the true cosmology is also same, is out there. And as we expect, this is really less than one or about the 1 or 2% the level, and we actually measure very precisely. Or second, there is no guarantee whether our the fiduciary cosmology is exactly same like the out there in the true cosmology. We actually keep using our template cosmology, but we actually assume the true cosmology out there is different with different cosmological lambda, and we actually again reproduce exactly in the 2%. And we actually repeat the same experiment with the other end. So here actually what I would like to say is that as far as the precision requirement for the future survey, we actually reach that the accuracy. So I jump to all the mapping of the cluster. So here is a conclusion. So conclusion is that we are actually now going into the era. We actually facing the future challenge from the precision cosmology. At the time of the data release, we probably understand for the cosmic acceleration whether we need dark energy component or gravity is modified. So requirement to the theorist community, and we have to understand very well all the theoretical modeling of the invisible large-scale structure, and throughout our whole effort, and we indeed understand precisely the mapping from the real space to redshift space. Eventually, probably in the 5 years' time, we can provide very precise measurement to the community. So I wrap up my talk.
Okay, thank you, Professor Song. So, any questions? Questions, please. Professor Kumar?
It's not so, I'm still not so clear that you have got two, how are you breaking the degeneracy between the left-hand side and the right-hand side of the Einstein equation? Which means that you have the geometry modified on the left-hand side, or you have got the matter, and not, I just still miss the point, how the power spectrum is being used to break that degeneracy.
Yes, so let me actually explain to the point. Okay, here. So actually, it's a very good question. So then I have to say this way. So in this talk, I didn't mention about actually in the cosmological side, there are two different observables. The one is geometry, and the other is structure formation. So basically, once you analyze the large scale structure data, you will have geometric information, angular diameter distance, and then expansion history. And also, as I present if you are smart enough, we can extract structure formation. Now, when you have some expansion history, then I assume that you understand very well background expansion throughout this experiment. Now, we actually combine this. When you actually solve some like Bianchi identity of the structure formation in the second order equation, which is completely determined with a known expansion parameter. So if there is no crazy the theoretical model like gravity is modified or anything like that, so technically means that once you understand geometrical the history, then you can actually the predict the history of the growth function is very well. Now, in that sense, when you actually based on this the expansion history, you also the amount of growth function you actually. But if you measure something different from this, what is actually meaning? It's a possible deviation. That is actually the first our plan. But second plan is actually the more challengeable. The second plan is I didn't quite mention clearly about this. Here in the left side, when you actually observe the galaxy survey, you have information of the fluctuation of matter quantity. You decide delta, you decide peculiar velocity. Now, when you actually make the another types of measurement of the weak ranging survey, the light actually bended due to geometrical factor, right? The geometric combination of the curvature parameter and the time dilation. So technically means that the combination of the geometrical information which revealed the weak ranging. So then you understand very clearly now. If those actually is done, then you actually put your observed quantity in the both sides, and then combine this. Whether this is consistent with the prediction of the Einstein's prediction, then GR is there. But if its equivalence is broken, so technically means that gravity probably should be modified. So that is two different.
So yeah, that is what I was missing, is that you are planning to combine it with the weak lensing.
Yes, yes.
I mean, that's an important step.
Yes, right. But in the timeline of the data release, and then the DESI will initiate from the 2019. So probably I involved in the growth function the test based on background. This is our first plan. And then soon LSST will be launched early 2000 going through in the mid 2000. When this actually rebuild released, then finally we can actually combine those together, and we actually so our group actually commit two experiments at the same time.
So any questions? If not, Professor Song, again, thank you for your presentation. Yeah. And the next talk will be Professor Sushko from Kazan State University. He title of his presentation is Cosmological Scenarios in Horndeski Theory.
Yeah.
Ну, что тут?
Да.
Okay. So, good afternoon. First of all, let me express my deep gratitude to the organizers and personally to persons who, with him I was in correspondence, beautiful Aliyah, Eric, where is he? He's absent, and Baurjan. It's very nice to visit Kazakhstan. It's not my first visit, but I visited Almaty several times, but it's my first visit to Astana. So nice place, nice city, new, absolutely new, no dust. Yeah. Okay. I'm a theoretician, and I will speak about some theoretical models, about some theoretical cosmological models, and these models are as general as possible with one side, but nevertheless, I will speak about more specific models. Namely, I will speak about scalar tensor theories of gravity, and I will consider Harandesky theory. Well, this is collaborators and some papers I refer to. This is a plan. Well, just recently you speak about the necessity that we should modify, or we should correct our approach to the theory of gravity, and this is because of great success, great advantage in observational. What? Okay, thank you. Well, and as you see now, we should we have new data, and we should explain the modern acceleration of the universe, and also we should at the same time we should explain the inflationary stage of the universe, and the dream of each theorist is to construct the theory of everything. And in 17th century, Newton constructed the theory of everything, but everything was a sun system at that moment. And after some study, it was clear that for example, everyone knows that the Newton theory does not describe Mercury, shifting of Mercury perihelion. So after this, Newton constructs new theory which describes everything. I mean, gravitational theory. But now we know that Einsteinian theory also has some lacks, and it is impossible to describe and to explain us some properties in evolution of the universe. So we need to find some unknown forms of matter. For example, in order to explain the dark energy, or we need to modify the theory of gravity, which we use now, the Einstein theory of gravity, as you said before. So I will discuss some specific approach to modify the theory of gravity, and I will discuss the scalar tensor theories of gravity. And here several words about scalar fields. Scalar fields, I mean fundamental scalar fields, gravitational scalar fields, are not found yet, but people believe that they should exist. And there are a lot of arguments for existence of scalar fields, and of course one of the very important argument is, where is it? So scalar field plays the role of inflaton in provide us inflationary stage. Well, how we can construct this scalar tensor theory of gravity? We can consider scalar fields which are minimally coupled to gravity. Minimally means that we consider the action of the Lagrangian of the theory consisting of two unconnected parts. So this part is purely gravitational Lagrangian, and this part is purely a scalar part of the Lagrangian. And also we can add some matter part here. So in this case, we have scalar fields which is minimally coupled to the gravity. Minimally means that via Einstein equations and left hand side of these equations are purely geometrical, and right hand side is purely scalar field or matter part of the equation. And but even here you can generalize your approach. You can consider as general models as possible. For example, we can consider now it's quite popular FR series of gravity, so you can generalize separately this part or this part, and for example, you can consider something like K essence series of a scalar field with some generalized kinetic part of this model, and so there are a lot of ways to construct general modified series of gravity even in this approach. But the other way is to consider non-minimal coupling of scalar and curvature, and quite a general form of this Lagrangian is the following. And non-minimal means that we have the term like this one. So it's direct interaction between scalar and curvature, and this is well-known scalar tensor theory as general as possible. There are three arbitrary functions here. One function is potential, and two other are arbitrary functions. But it's known that there is some mathematical trick known as conformal transformations. So we should transform the metric to do some conformal transformations. We should redefine the scalar field, and after this we obtain the theory of minimal scalar field, and with some new effective scalar field and with some new effective potential of this theory. And it's important that the kinetic term could be unusual here, so it could be positive or negative kinetic term after these transformations. But main information about scalar field is in this effective potential. Well, usually I show this slide, and you can consider as a very general model of non-minimally coupled scalar. For example, you can consider the theory with arbitrary function of scalar and curvature. So I don't know if there exists some more general, but anyway, after some conformal transformations, you again obtain the model with two effective scalar fields, and these scalar fields are minimally coupled to the curvature. And again, all information about scalars are hidden in the potential function. So some intermediate remarks are the following: that if we consider non-minimal scalar fields, this theory is conformally equivalent to the minimal one, and with some effective potential. And because of this, all information about scalar field and ultimately about the evolution of the universe is hidden, is encoded in the potential of scalar fields. And because of this, a lot of cosmologists try to construct an appropriate model of cosmological evolution with some appropriate form of potential, of scalar potential. And this problem is known as a problem of fine-tuning of this scalar potential. Well, because the potential is arbitrary function, you can try. There is a hope that you can find some unique potential which will describe the whole stage of the cosmological evolution. Well, so now about the other way to generalize the scalar tensor model. One way is to generalize this curvature term. So instead of curvature term, the standard Hilbert-Einstein Lagrangian, we can consider some term describing non-minimal coupling of scalars with curvature. But there is also the other way. The other way is the following. We can generalize the kinetic term of the scalar theory. What does it mean? It means that we can consider some function which include the terms describing connection between derivative of scalar field and the curvature. In this case, this generalization is known as non-minimal derivative coupling generalization. Some remark is the following. If you consider such generalization of scalar tensor theories, practically always you will face with the problem. You obtain theory with higher derivatives. If you consider some non-minimal coupling, you obtain the higher derivatives in the field equations of your model. And it's not good from the point of view of classical theoreticians. The dynamical theory should be of second order at last, at most. But about scalar tensor models, you see that a long time ago in 74, Harandesky derived the action of the most general scalar tensor theory with the second order equation of motions. This model was forgotten for some time, but now it's quite popular, and there is some very general Lagrangian. It's Harandesky Lagrangian, and you see that there are some very messy terms here. So now it's people use this definition L2, L3, and L4, L5, and you see that there are 1, 2, 3, 4 arbitrary functions. 4 arbitrary functions, and it's functions of 2 arguments. X, this is just notation for kinetic term, and phi is a scalar field. So this model is extremely general because we have 4 arbitrary functions in this model, but the algebraic structure of this model is that field equations of this theory are second order only. Now about, well, of course, because of this generalized, because this theory is so general, it's not so easy to work with these models. And if you are interested in some exact solutions and some other algebraic properties of this model, it's quite difficult to treat with this model. And because of this, people consider some specific subclasses of this model. And one subclass is so-called FAB4 subclass of the Horndeski theory. Well, I am not native English-speaking man, so it was strange for me. What is FAB4? But American people knows that this is Beatles, yeah. So it's fabulous 4. And FAB4 because this subclass contains 4 terms, the Lagrangian of this model, 4 terms plus, of course, cosmological constant. So it's 5/5 term. And this is John, Paul, George, and Ringo. So because this notation means the name of this FAB4 guys. Well, so this is some mathematical expressions. Why this model is interesting? Well, because this model is very interesting and very popular, because one of the serious problem of modern cosmology is the value of the cosmological constant, the present value of cosmological constant. This cosmological constant, well, the universe now is accelerating, yes? And the best model and the simplest model to explain this acceleration is just cosmological constant. You can insert cosmological constant in your Einstein equations, and you obtain the de Sitter phase, so no problems. But the problem is that the observed value of cosmological constant is extremely small. In comparing with theoretical predictions. Theoretical predictions, they come from quantum field theory. And if you estimate the energy of vacuum energy of vacuum polarization, you will obtain the cosmological constant which is greater than observed and greater on 123 orders. So it's a huge discrepancy, and nobody knows now how to explain this discrepancy. And one way is the following. And in the FAB4 subclass of Horndeski theory, there is some explanation. Explanation is the following. This model has a screening property. What is a screening property? Screening property is the following. Even if you insert by hand the cosmological constant in your model, and this arbitrary value, it could be as large as you want. Nevertheless, in this model, there exists the solution describing Minkowski space. So you see that however large lambda is, Minkowski space is always a solution, and so one may hope that we also can obtain not exactly Minkowski solutions, but some variation of these solutions with appropriately small value of effective lambda term. So this is one of the very nice properties of the Horndeski theory. I will discuss the other subclass of the model. This is a theory with non-minimal kinetic coupling. What does it mean? It's very simple generalization of the scalar tensor theory, and generalization is the following. This is kinetic term, this is potential, this is matter, action of some matter stuff, and generalization is here, is given by this term. This term describes the coupling between derivative of scalar field and the Einstein tensor. So the curvature, here the curvature is given as the Einstein tensor, as a component of Einstein tensor. And you see that this is after some standard procedure, you will obtain the field equations of this model. And it's important that these field equations are of second order. Again, it's general property of Hromdeski theory. Well, these equations are not Einstein equations. You can say that this is modified Einstein equations, but I don't like. I use these words, but in fact, it's not even Einstein equations, because it's just formally I divided into two parts. But you see that left part is purely geometrical, but right hand side is also contain some curvature. Where is it? Some curvature terms like this one and this one. So in this theory, you cannot divide geometry and matter or scalar field. So it's important. Now about cosmological applications of these models. I will discuss only cosmology here. And if we consider the simplest model, so this is flat Friedman metric, field equations now are the following. Okay, I will dub these equations as modified Friedman equations. But you should remember that again, you see that Hubble is here and Hubble is here. So actually, it's something new. And all modification is hidden in these terms. All modification is hidden in these terms. Well, yes, of course, who is working with scalar field theory models knows that if potential is constant or equal to 0, you have some first integral, but it's not to do your life more easier, unfortunately. Well, some very simple situation just to illustrate for you some features of this model. So the simplest is the following: no potential term, no non-minimal kinetic coupling, just massless scalar field. Of course, this situation is well known. In this case, you obtain the following exact solution, and this is solution which the scalar field effectively played the role of stiff matter with parameter of equation of state omega is equal to 1. So effectively it's like a stiff matter with speed of sound equal to speed of light. And in this case you have some model, and this model has an initial singularity. And the scalar field is proportional to log of t, log of cosmic time. Well, now let's consider the other simple model. It's a simple model, but it's already non-trivial model. You see that we have some generalized kinetic term here. and we have no, you see, epsilon is equal to 0. So we have no normal kinetic term in this model. So it's purely modified theory with modified scalar field. And but this model is still very simple, and it's possible to obtain some analytical solutions in this case. And we have the following solution. This solution is a little bit different from the previous. I mean, power here is different, but again, this model is with the model with an initial singularity, so it's a singular model. But interesting here is interesting that the scalar field is proportional not log t but t, so proportional to the cosmic time. And also it's I want to draw your attention to this fact. This parameter is parameter describing non-minimal coupling. Is it stands into denominator, so you cannot go to the limit eta equal to 0. It's not analytical situation because the Einstein equation and modified Einstein equation are not linear, and this is qualitatively new solution, and there are no limits, analytical limits. Of course, you can put this parameter to be equal to be 0 in the initial Lagrangian, but it's impossible to do the same in the exact solutions of these equations. So this solution is qualitatively different from the usual situation with scalar field. Well, now if we consider more general situation with usual kinetic term and with modified kinetic term, we obtain the following result. Asymptotic for large times is the following. It's asymptotic. You see the model with non-zero parameter has the same behavior like that with 0. So evolution is, if we try to use this model to describe the real universe, now the influence of this non-minimal coupling is, we can neglect this influence. But what about early times? And it's, the evolution depends on the sign of this coupling. And you see that if eta is negative, we obtain the singular model like before. But for positive eta, we obtain nothing but de Sitter model. Of course, quasi-de Sitter model. It's a model in the limit of t equal minus infinity. So this is a quasi-de Sitter model with the metric has a de Sitter form, and h, so de Sitter parameter here, is given like this one. And again, you see that the parameter non-minimal coupling parameter stands into denominator. So we cannot just put by hand eta equal to 0. It's absolutely new solution. Well, this is just some numerical solutions of this. So I can say that this is exact solutions, but just numerical solution of some differential equations, well, with some initial parameters. And you see that at this moment I can conclude that the model with non-minimal kinetic coupling has a de Sitter phase without any potential. So it's very interesting feature of this model. So we need no potential. We need any potential to describe the quasi-de Sitter stage of the universe. So we need no potential to construct inflationary stage of the universe. But of course, this is some toy models, and we need to do to go further. And very quickly, I run through some other situations. The situation is the following. Let's add by hand the cosmological term. Why we should do it? Because the cosmological term it's vacuum energy, so we should to input this term into the Lagrangian. And it's interesting here that in this case we have exact de Sitter solution. It's very simple. When scalar is constant, all derivatives disappears, and we obtain the usual de Sitter solution. But in this case, there is a second de Sitter solution, also exact de Sitter solution. When scalar field is not constant, it's proportional to cosmic time. But anyway, we obtain the de Sitter solution. Well, this alpha here is the exponential, just exponential. So this is de Sitter solution, and you see that this de Sitter solution, the Hubble is the following here, and again, parameter eta stands into the denominator, so we see this feature. Well, because we have two exact de Sitter solutions. If we if we will study some phase space of this model, we obtain the following solutions. A solid line means the numerical solutions. These solutions describe two asymptotics. So initial de Sitter and final de Sitter. So in this simple model, universe evaluates from one de Sitter stage to the other de Sitter stage, and this gives us hope that we can use this model to describe the early inflationary stage and the present acceleration and the model. Well, now I want to consider because we discussed the scalar field. The scalar should possess some potential, and it could be that the potential just destroyed this nice picture with two de Sitter phase. Let's consider the role of potential and in this model. Okay, the simplest case is the power law potential, and even more simple is the square potential. Squared potential. So let's consider the model with the squared potential, at least here, and you see that if we consider this potential, again, we obtain the early time, the primary kinetic inflation. So this inflation, again, is kinetic because this Hubble parameter contains the non-minimal coupling parameter in the denominator. So this is typical situation for this model. So without any fine-tuned form of potential, again we obtain the kinetic inflation here, and but now it's more interesting the late time behavior of this model. And late time behavior is the following. Well, we have several various asymptotes here. One is usual oscillatory asymptotic, or what does it mean, oscillatory asymptotic? This is graceful exit from inflation. So your model starts from inflation and then finishes just some oscillations which could create some particles of usual matter, if we will consider the interaction between scalars and usual matter with usual vacuum. And also there is the other choice. There is the other choice of this dynamical system. There is a late time quasi-de Sitter asymptotic, or you can say that this is secondary inflation in this model. And again, each time I draw your attention that eta, this parameter of non-minimal coupling, is in the denominator. So this is very specific solutions of this model. Well, this is some numerical simulations, and it's also quite interesting simulations. For example, look at this. These simulations are given for various initial conditions, and this point, this part of this graph is the initial de Sitter stage. So you see that Hubble parameter is constant, but it's quasi-constant, of course. It's constant, but then after at some time evolution change its character, and we obtain some oscillations of Hubble parameter. And the other branches, the following. After this constant, the Hubble very quickly goes to this constant. But what does it mean very quickly? If you will use dimensional units, this is 14 billion years. So not 14, 7 billion years. So of course it's a joke. But you can find some appropriate value for these parameters to obtain, namely, this volumes. There is also the little bit other behavior of this model, even more interesting, at least for me. You see that we have initial quasi-de Sitter stage, and then some exit to the other stage. What is this? This is plateau. This is plateau, and the length of this plateau depends on the initial parameters of the model, depends on the parameters of phase diagram. Exactly speaking, depends on the trajectory on the phase diagram, and this plateau is effectively like a quasi-de Sitter stage. But this because Hubble is constant on this plateau, but after some period, again we see that there is an exit from this plateau. So after the stage of acceleration, the universe goes to the oscillatory phase. So again, this is graceful exit from the stage of secondary inflation. Well, I skip the case of Higgs-like potential. Also, you can consider various potentials here, and we consider exponential potential. We consider Higgs-like potential is just interesting that Higgs-like potential, if we consider the model with Higgs-like potential, we obtain the same situation. That is, we have initial quasi-de Sitter phase, and we have several variants for late time evolution of the universe. One scenario is quasi-de Sitter scenario. So you see, this is phase diagram for scalar field. This is just directly graphs for Hubble parameter, and you see that Hubble goes to constant. This is quasi-de Sitter late time evolution, and also in this model we obtain well-known some variants of other scenarios with acceleration. This is B creep. So in infinite time, the Hubble goes to infinity, and there are some trajectories on the phase diagram which give us this scenario. And also we have the little rip, so-called little rip evolution of the universe when Hubble goes to infinity in infinite time. So this model very easily to describe as several stage of in universe evolution. Without any special tuning of potential, we obtain the early initial inflationary stage and late time acceleration. And moreover, we have the without any special conditions, we have exit from we have transition from one stage to the other. So without some special form of potential. And now role of matter, I skip role of matter. I just show you some estimations. Well, if we will consider some, we took into account some standard numbers for inflation, for example 60 e-folds, and this is duration of inflation stage. We can estimate this parameter as follows, and you see that this is, I forgot to say that this is dimensional parameter, and if we use length, it's 10 minus 27 centimeters. It's 6 order higher than Planckian order 5 minutes. Okay, it's 6 order higher, and in energetic scale, it means that 10 to 13, huh? Yeah. Graph, I mean. So it's quite nice number. It's not less than Planckian scale. It's very good, and at this moment we cannot to check this value, of course. Well, now screening properties. I have 4 minutes, 3 minutes to explain you the screening properties of this model. So again, if we consider the this ansatz for cosmology, this is field equations of field equations, and you see that we can find the first integral of this model. This is first integral of this model as before, and Q is a scalar potential charge or Nusselt charge. It's because there is a shift symmetry. There are no potential and there is a shift symmetry. We can just to shift the scalar field, and because of this we have some Nusselt charge. And you see that if Q is equal to 0, we have two solutions of this very simple equation. One solution is, and I will say that this is GR branch. So just psi equal to 0, psi is phi dot. This is phi dot. So, and in this case, if we consider this branch, we obtain the following equation for Hubble. But here we have the other branch also. If this expression in parentheses is equal to 0, and we obtain the screening branch. What does it mean? You see that if A goes to 0, if we consider GR branch, and A goes to 0, we saw that oh, I'm sorry. A goes to infinity. I'm sorry. A goes to infinity. We saw that H squared is proportional to lambda, and this is a well-known property. And this means, in modern language, it means that our universe is accelerating because H is constant and H squared is proportional to lambda. But this is a problem because lambda is very huge, very huge. But look at this screening branch. In this case, we obtain the same algebraically the same expression. But if A goes to infinity, H squared is proportional to this term. H squared is proportional to this term. And now this term plays the role of cosmological constant. So, if we have non-minimal kinetic coupling, we obtain that it could play the role of cosmological constant. And this is nothing but the screening effect of this model. So, 1 minute, just for conclusion. So, but you see that you can take the cosmological constant as large as only possible. Its value could be arbitrary, but anyway, we have a screening branch of this model. So, the evolution could be just slightly differ from the Minkowskian space. Well, then you can see that if Q is not equal to 0, you have the same behavior of this model. So it's not important to discuss the details of these equations. And so let me just show you some summary. And the summary is the following. First is the following: the non-minimal kinetic coupling provides an essentially new inflationary mechanism, which does not need any fine-tuned potential. It seems to me very important. Also, it's quite interesting that the model provides a natural mechanism of changing of epochs without any fine-tuned potential. And and what is most important? Well, I have no time to discuss the stability of this model, and it's very interesting that all solutions shown here are ghost-free. So it's very important if you consider various modifications of the scalar of the theory of gravity. You practically inevitably faces with this problem. You obtain some ghosts because you obtain new degrees of freedoms, and one of degree of freedoms is ghost. So in these models, it was checked that all scenarios are ghost-free. Thank you for your attention so much.
Thank you, Professor Srushkov. Any questions, Professor Kumar?
I have a couple of questions.
Okay.
One of which is that in one of the solutions that you showed, where eta, depending on the sign of eta, whether it's positive or negative,
Yeah.
you have the inflationary scenario and then the standard Robertson-Walker evolution. And it's not clear that how you make the transition from eta negative to eta positive. I think one of the solutions that you presented had this sinusoidal term, and that seemed to make the transition from, I guess, inflationary scenario to the ordinary scenario. So let me just ask you, how exactly is that the way that you are making a transition from a positive eta to a negative eta? And I have one other question. I'll just ask you that question too, and you can address them in whatever order you like. In addition to getting the inflation, one of the things that is done during the inflation is that you also generate perturbations. Those perturbations then in turn are amplified and form structure. I don't see anything in any of the models that you describe how perturbations are produced in any of these models. So,
thank you. First questions is very simple. I see that you was hearing my talk very carefully, and actually, I show some cases with positive eta and negative eta. Yeah, but in fact, this is parameter, and from the very beginning, this parameter is undefined. So it's your decision and which parameter should be. And after some investigations, you should decide which parameter is good, which not. In fact, all good properties of these models are for positive eta. Yeah. So you are absolutely correct, right? Yes, asking me about it. I just have no time to consider various situations, but in this model, we consider ultimately we consider positive eta. About perturbations, now it's my
generating part of it.
yes. Well, now it's a part of our joint project with Alexey Strabinsky, and now we are working and a little bit slowly working about it under this. But anyway, works is under construction, and I have only some previous information about it. I only can say that the character of perturbations are drastically changed in the early times of evolution because of this non-minimal coupling, and drastically changed. In the inflationary stage, you see that it's kinetic inflation, and this kinetic term play the most important role and change the evolution of perturbations. So it's only I could say now. This is I know that something will be changed, but it's under consideration. Yeah.
Okay, Professor Chechin.
Thank you. I want to say the following: that I had 5 questions for you, but during your
maybe one.
You answered 3 of them. That is why I have only 2 questions.
Okay.
First of them, it is a well-known result that situation that this very known situation.
I hear you. Yeah.
Yes. For solving Einstein equations, it is necessary to add to them coordinate conditions. Координатные условия. Yes.
Well. We are working in.
My question is, why do you think that that condition that you took, or when you consider the flat space, k equals to 0, why it is possible to use for this Korandesky gravity?
It's a very simple question because we are working in this ansatz. Because we know that our universe, because of observational data, is highly homogeneous. So it's just a model. We are working in homogeneous model, and homogeneous and isotropic model are Friedman models.
So in principle, yes,
Robertson. So it's just ansatz because we consider cosmological model. And of course, next step is to consider perturbations. But we start with Friedman flat model.
Did you consider another very important cosmological effects, such as gravitational lensing, such as
no, because again, it's I should to consider some perturbed solutions of this model. Not yet.
In principle, it will be very important.
Yeah,
I think you know this rather well, but never.
Thank you for your question, but the answer is not.
Okay, thank you, Professor Chechen. So, more questions? If not, Professor Strushkov, thank you for your talk.
Thank you.
Now we have free time for coffee breaks, for nice coffee break with snacks, and see you in 20 minutes here.